This video is going to show you how to identify functions as linear or exponential by first classifying the sequence and then writing both the explicit and the recursive rules. If you're in my class, please turn to page 25 in your packet, pause the video, and try the following problem. Okay, so after you've tried this on your own, you should realize that actually both students are correct. And let's take a look. Student A says the pattern is there are 3 bacteria at the beginning and then they are doubled every hour. And sure enough, if we multiply by 2, that's exactly what's happening. So student A is correct. Now student B says the pattern above is 3 times 2 to the power of t. So 3 times 2 to the power of t. And then if we substitute in 0, 3 times 2 to the 0, well, 2 to the 0 is 1. 3 times 1 is 3. That's what's here. Check. 3 times 2 to the first. 2 to the first is 2. 6. Check. 3 times 2 squared. 2 squared is 4. And you can see that student B is correct also. The difference is that student A, we say, took a recursive approach. And what that means is that they found the pattern and they described the beginning amount, and then they described what the pattern is. Student B took what we call an explicit approach. An explicit approach means we are writing an explicit formula, okay? So here, this function, like bacteria at time t, this is our explicit formula. We can explicitly find any value at any time t versus the recursive approach, which is the description of a pattern. So let's take a look at page 26. Page 26 gives us some notation. Let's take a look at it. For arithmetic sequences, and that is pronounced arithmetic, not arithmetic, those are linear sequences. As a reminder, arithmetic sequences, linear sequences, have an addition or a subtraction pattern. If I'm writing a recursive formula or a recursive rule, I'm going to start with a starting value. Now, normally it's 0. It could be 1 or 2 or whatever. So I'm going to state my starting value. Then I'm going to say to find the nth term, I'm going to take f of n minus 1. And if you think about it, that's just the previous, write this down, the previous term. And I'm going to demonstrate this in our first example. Right. So that's how we're going to write a recursive rule. We're going to state the first value, then we're going to state to find the next value, we take the previous value, and we add the rate of change. Now, an explicit rule for arithmetic or a linear sequence is just going to be a y equals mx plus b. Nothing new there. For a geometric sequence, as a reminder, geometric sequences are like exponentials, and they have a multiplication or a division pattern. It's going to look really similar in the sense that I'm going to start with f of 0 or whatever my first term is. And then to find the next term, I'm going to take f of n minus 1. Every time you write f of n minus 1, please write this in your packet, I want you to think previous term. And then I'm just going to multiply it by the rate of change. For an explicit geometric rule, I'm going to use a times b to the x, where a is the starting value and b is the growth or decay rate. Nothing new there. Okay, so what I'd like you to do is take a look at our first example. We've got this sequence, and I look at it, and I see that I am adding 3 every time as I go down. Therefore, this is an arithmetic sequence because it's plus 3. So to find the next term, I'm just going to write it out, add 3 to the previous term. So my recursive rule, my first term is 0. So there's f of 0 equals 5. Now, I want to show you something. If I was looking for f of 1, I would need f of 0. That's the previous term. So like here, if this is 1, 1 minus 1 gave me the 0, and then I'm just going to add 3 to that. So the second half of my recursive rule is f of n equals f of n minus 1 plus 3. So let's say we were looking for the fifth term, just for fun. If we were looking for the fifth term, I would have f of 5 minus 1 plus 3. Again, I'm just using my formula. Nothing tricky, just the formula. F of 5 minus 1 becomes f of 4. That's the previous term. So to find the fifth term, I need the fourth term, which I don't have in my table, but I can find pretty easily. So I'm going to take the term before that, which is 14, and just add 3. So that's 17. So my previous term is 17 plus 3 would give me 20. So that's how this recursive rule works. So to find the nth term, I start with 5. This is my description of the explicit formula. I start with 5, and I'm going to add 3 n times, because 5 is like my y-intercept, and 3 is the slope. We're going to do a few problems together, and then you're going to try a few on your own. What I'd like you to do, just for a minute, pause the video, and all I want you to do is to determine, is number 1, arithmetic, geometric, or neither, and have a reason. You should have found on your own that problem number 1 is geometric. Why? To find the next term, I'm just going to multiply the previous term. Well, I spelled previous wrong. That's embarrassing. By 2. Okay. So here, my recursive rule actually starts with 1. So my recursive rule is going to be f of 1 is 5. There's my starting value. To find any other value, I'm going to need the value before it, and I'll multiply it by 2. And that's the recursive rule. Now, to find any term, I'm going to start. Well, now here's the trick. I don't have an a value here. A happens when it's 0. So to write the recursive rule, I don't need it, but to write the explicit rule, I do. So let's think. If this is 0, if the pattern here is times 2, I'm going to go up. This is going to be 5 halves. So I'm going to say start with 5 halves, multiply by 2 n times. That can be x times. Let me get x. So my explicit rule will be y equals 5 halves times 2 to the x. It could also be f of n equals 5 halves times 2 to the n. It's up to you. So again, please pause the video and determine if it's arithmetic, geometric, or neither. You should have determined that this was neither. At first, it looks like there's going to be a multiplication pattern because 3 times 3 is 9. But the problem is it's 9 times 9, which is 81. And that's not a consistent multiplication pattern. It's a pattern, but it's not where the same rate of change every time. So we don't need to do the rest. All right, so what I'd like you to do, again, pause the video, turn to page 27, and just determine, is each problem arithmetic, geometric, or neither? Okay, so let's see what we got. Hopefully, number 3, you see that there is no pattern here. You see it first, you're like, well, maybe this is like +2. Oh, and then this is +4. Ooh, and that's kind of like a neat pattern, but it's not a consistent arithmetic pattern. So it's neither. For number 4, hopefully you saw that we're just subtracting 9, making it arithmetic. So what I'd like you to do is pause the video, and can you do numbers 2 and 3? Hopefully you wrote, to find the next term, we're just going to subtract 9 from the previous term. And for the recursive rule, hopefully you wrote f of 1 is -8. F of n is f of n minus 1 minus 9. Okay, now to find the nth rule, the nth term, we need the starting value, and I don't have that 0 value here. So I'm going to back up the pattern, and I'm going to see at 0, that's going to be 1. So I'm going to start with 1, and I'm going to, not add. I'm going to subtract 9 n times. So one way we could write this rule would be f of n equals 1 minus 9n. If you're a big mx plus b person, you can write it negative 9x plus 1. They're virtually the same thing. Hopefully for number 5, you realize it has a multiplication pattern also. The multiplication pattern is multiply by 3. So to find the next term, multiply the previous term by 3. Negative 3, sorry, whoops. Okay, so we're starting with f of 1 equals 2. What do you think f of n will equal? Hopefully you said it's the previous term, which is f of n minus 1 times negative 3. And I'm just going to put the negative 3 in parentheses here so it doesn't look like minus 3. Okay, again, we have the problem. To find the nth term, I need the 0 term. So I'm going to divide by negative 3, and I'm going to get negative 2/3. So I'm going to start with negative 2/3. I'm going to multiply by negative 3 n times. So a times b to the x, f of n, is a times b to the independent variable. And if you use x and y, that is fine. What I'd like you to do is to try all of number 6 on your own. Okay, hopefully you've paused the video and you've done all of number 6, and you realize that number 6 has a division pattern. What we're doing here is we are dividing by 5. So this is a geometric pattern. To find the next term, take the previous term and divide by 5. Okay, so our recursive rule will start f of 1. We always need a starting value is 10. To find any term, take the previous term. And now here's where I'm going to be like, I don't really want to be like divided by 5, because like I could do that, but that looks really ugly. I am not going to do that. I'm going to think dividing by 5 is like multiplying by 1/5. Now, if you want to write all over 5, I am not going to mark it wrong. I'm just not going to write that down because I think this looks better. Now, again, we have the problem to find the nth term. We are missing that 0 term, so this one's not so bad. If we back the pattern up, we find that our first term is 50. So start with 50. And I'm going to say multiply by 1/5 n times. So my explicit rule, it's like just like a times b to the x. I have my a, I have my b, and I have my independent variable. Hopefully this helps you feel confident on writing explicit and recursive rules with arithmetic and geometric sequences. Remember, arithmetic and geometric sequences are just like linear functions and exponential functions, just with some slightly different notation. Go ahead and start the homework on pages 28 and 29. I would suggest you pause the video. I'll go through 2 problems just to make sure you're okay. All right, hopefully you've tried this on your own. And number 1, I can tell, is a +2 pattern, making it linear. I'm just going +2. All right. So now the recursive rule, I'm going to start with that f of 1 equals 3. And then to find the next term, I'm going to take the previous term and add 2. For the explicit formula, I need the y value at 0. So I'm going to have to back the pattern up. And I find my y-intercept is at 1. And really, if you wrote y equals 2x plus 1, I'm marking it correct. You could also write it as f of n equals 2n plus 1 or 1 plus 2n, whatever you prefer. The answers for these problems will be posted online. Please check and annotate your work. Again, homework pages 28 and 29.